We're going to introduce a new force this time. Whenever an object is immersed or floating on or immersed in some fluid, there's a force from the fluid on that object, and it's called the buoyant force. So let's imagine this situation. Imagine just a cube with a length of L meters on each side of the cube, immersed in some kind of fluid. And the top side of the cube is a distance d meters under the top level of the fluid, and then obviously the bottom surface is at a depth d plus L meters below the surface. So there's a force from the water pushing down on the top surface, and there's a force from the water pushing up on the bottom surface. That force pushing up is simply because the fluid molecules here are bouncing around, and sometimes they will bounce off the bottom surface, and whenever they bounce off the bottom surface, that constitutes a tiny little upward push on our cube. And the total of all those pushes amounts to some kind of force on the bottom side of the cube. So just for reference, obviously the top surface and the bottom surface of this cube have areas of L squared, square meters, and of course the volume of the cube is L cubed, cubic meters. And there are two forces from the water on the cube, a force on the top side of the cube pushing down, a force on the bottom side of the cube pushing up. And of course we can, since those forces are distributed over the top and bottom surface areas, we can associate those forces with pressures. And the fluid pressure at the top side of the cube is just the atmospheric pressure plus the pressure due to the fluid, d meters deep. And similarly, the pressure at the bottom of the bottom side of the cube is just atmospheric pressure plus the pressure due to the fluid, and being at a distance d plus L meters below the surface. Right? The pressure due to the fluid is always density g depth, and on the bottom side of the cube, the depth is d plus L. So the net force acting on the cube is, I had this backwards, sorry. It's the force on the bottom pushing up, and then the force on the top pushing in the opposite direction, pushing down. Well, we can associate this force with a pressure. Remember that pressure is force per area, so pressure times area gives us a force. Pressure at the top times area of the top surface gives us the force on the top surface pushing down, pushing in the negative direction, and then area of the bottom surface times pressure at the bottom side of the cube. That gives us the upward force on the bottom side of the cube pushing up. Now let's write this out in detail, and we'll actually come up with a pretty simple rule. So the net force, and remember that's net force from the fluid on the cube, is first area times pressure at the bottom. Remember, area of each side of the cube is L squared. And then pressure at the bottom is all that. So let me write it out here. atmospheric pressure plus the pressure due to being deep in the fluid, density of the fluid, G, and then on the bottom side, you're at a depth of D plus L. That's the pressure, that's the force at the bottom pushing up, and then minus force at the top pushing down, which is area times pressure at the top. Area is L squared. And then the pressure at the top is atmospheric pressure plus the pressure you get from being deep in the fluid. And that contribution to the pressure is density of the fluid, G, times depth. And on the top side of the cube, the depth, you're at a depth of just D. Now there's a lot of stuff that cancels out here. This times this gives us a factor of L squared atmospheric pressure, and then here's minus L squared atmospheric pressure. So those things just cancel out. And then here you've got a factor of L density GD, and then, L squared density GD, and then L squared minus L squared density GD. So this minus L squared density GD cancels out the plus L squared density GD. And now all we're left with is L squared density GL. L squared times L is L cubed. L cubed is, remember, just the volume of our cube. So the net force is the volume of the cube times the density of the fluid that that cube is immersed in. So we have density volume G. Well, density times a volume is a mass. Mass of what? This is the mass of the fluid that got displaced and pushed aside when we put that cube into that space. Right. This is the volume of the cube, but it's also of the volume of fluid. It's also the volume of fluid that was pushed aside to make room for that cube when we put the cube in the fluid. So this is the volume of fluid that got pushed aside, displaced, times density of that fluid. So this just gives us mass of the fluid that was displaced by putting the cube there. So the net force is mass of the fluid displaced times G. Mass times G is just weight. So this net force from the fluid acting on that cube that is immersed in the fluid is just equal to the weight of the fluid that was displaced by that object. And that's the buoyant force. And that's our slogan for buoyant force that you must always remember. Precisely everything that you do involving buoyant force starts with that idea. So I'll just write it here. Buoyant force equals the weight of fluid that is displaced by any object that's in that fluid or floating on that fluid. let's look at a couple examples of that. Imagine down in the riverbed, you've got a hippopotamus walking along the bottom of the river. And what are the forces on that hippo? Well, obviously there's the weight of the hippo pulling down. And the hippo is walking on the riverbed, so there's a normal force from this surface pushing up on the hippo. And then, of course, the hippo is immersed in water, so there's a buoyant force from the water pushing up on the hippo. And let's say we know the mass of the hippo, and it's 1,500 kilograms. And let's say, believe it or not, that we know the average density, the overall density of a hippopotamus, an adult hippopotamus. You know, they measure all kinds of things at the zoo, and that density turns out to be 1,030 kilograms per cubic meter. Now, with that information, that's enough information to figure out what the strength of this normal force is, because it's also enough information to figure out what the buoyant force is, and to figure out what the weight is. So let's figure out the normal strength of the normal force. We start by doing the same thing as always. Once we know what the forces are, write some algebraic expression that shows how those forces combine to give you the net force on the hippo. And as always, if we say up is the positive direction, then the net force is just a matter of adding all the positive forces and subtracting all the negative force. So the net force on the hippo is upward force of normal plus buoyant force minus the downward force of the hippo's weight. And the hippo is not accelerating. The hippo is not moving at all vertically, just staying on the riverbed and moving horizontally with a constant velocity. So no acceleration, so no net force. And since we're trying to figure out the strength of that normal force, let's rewrite this equation in a convenient way. This equation tells us that the normal force is just going to be equal to the weight minus the buoyant force. So let's calculate those two forces. To do that, we need to find the mass of the hippo. Well, no, we know the mass of the hippo. That's 1,500 kilograms. So mg is 1,500 kilograms times 9.8 meters per second, and that comes out to, let me get my notes. That comes out to, let's say, 14,000 or 14,269 newtons. Those are too many figures. There's a bunch of insignificant figures there, but we don't have to round off to the significant figures until we get to the end of our calculation. This is just an intermediate step. So that's the value of one force. Now what about the buoyant force? Well, what is the magnitude of the buoyant force? It's the weight of the fluid displaced. In this case, the fluid is water. So it's the weight of water displaced. Or in other words, the mass of water displaced times g. But as always in these fluid situations, we want to think of mass as density times volume. So the mass of water displaced is just the density of water times the volume of water that got displaced. Well, the water was displaced by the hippo's volume. So the volume of water displaced is the same as the hippo's volume. So density times volume is mass times g gives us the weight of the water displaced. Now we can put in the numbers if we figure out what the volume of the hippo actually is. We have enough numbers to do that. Remember that density is mass divided by volume. We know the mass of this hippo and we know the density of a typical adult hippo. So volume will simply be mass divided by density. Volume is mass divided by density, that is 1,500 kilograms over 1030 kilograms per cubic meter, and that comes out to 1.456 cubic meters. That's the volume of the hippo, and that's the volume that displaces water when the hippo is there submerged in the river. Well, that's the factor that goes right there. So now we can calculate the buoyant force. The buoyant force is the density of water, fresh water, which is about 1,000 or 10 to the third kilograms per cubic meter. Times the volume of the hippo, which is the volume that displaces water, the volume of the displaced water, 1.456 cubic meters. Times g of 9.8 meters per second per second. And when you put in all of those numbers, that's mistake. That is 14,269 newtons. The weight of the hippo, I previously said the weight of the hippo was that. It's not. It's not. The weight of the hippo is actually mass of the hippo times g. That's 1,500 kilograms times 9.8, and that comes out to 14,700 newtons. So, with that correction, now we know what these two forces are. Buoyant force, just the weight of water displaced, which you could calculate as density of water times the volume of water that got displaced times g. So the normal force is the weight 14,700 newtons minus the buoyant force, 14,269 newtons. And that comes out to about 431 newtons, or our data really only had a couple significant digits in each for each number, so we need to round it off to just 2 significant digits, and we'll call the normal force 430 newtons. But that's the basic idea, and we did all the same things that we've done every other situation where we're dealing with an object that has a bunch of forces acting on it. We just figure out what those forces are and figure out what the direction of each force is, then write down some expression that shows how the forces combine to give you the net force. And then we set it equal to mass times acceleration. Acceleration is 0 in this case, and now we've got an equation that we can use to find whatever it is that we're trying to calculate, the normal force from the riverbed on the Hippo. But in this case, in order to get that number, we had to first figure out the buoyant force, and for that we used the basic fact about buoyant force. It's equal to the weight of fluid displaced. Here's one more example. This time, not something that's totally immersed in the fluid like the Hippo was, but something that's floating. Now just imagine a piece of wood floating in some kind of fluid. Not necessarily water, just some kind of fluid. And like most floating things, part of it is submerged and part of it is above water. This piece of wood is just floating, just sitting there. It's not rising, it's not sinking. So it has a constant velocity, constantly 0 to be precise. But constant velocity means no acceleration, which means no net force. So whatever forces are acting on that block all cancel out, all add up to 0 net force, and the only forces on that block of wood are its weight and the buoyant force. So the net force is just if we take up to be the positive direction, the net force is just all the upward positive force minus all the downward negative force, and they must cancel each other out because the net force and acceleration of that block are 0. So what do we know? We know the buoyant force is now, in this case, equal to the weight. That's going to be the case for anything that's floating. Buoyant force equals the weight of the block, so I'll say mb here for mass of the block. Now let's write out a little more explicitly what the buoyant force is. The buoyant force is the weight of the fluid displaced, or mass of the fluid displaced times g equals weight of the block, which is mass of the block times g. Now, as before, we always think of masses as density times volume. So the mass of fluid displaced is just the density of the fluid times the volume of fluid that was displaced. Well, the volume of fluid displaced was displaced by this part of the block. It was the volume of fluid displaced is the volume of the submerged part of the block. however many cubic meters of that block are under the top level of the fluid, that's the volume that displaces, shoves aside water, or shoves aside the fluid. So that's the volume of the fluid that was displaced to make room for the submerged part of the block. Density times volume gives us the mass of the fluid displaced, times G gives us the weight of the fluid displaced. Weight of fluid displaced is the buoyant force, and that's equal to weight of the block. Let's write that mass as also density times volume. That's going to be density of the block times the volume of the whole block. Times G. Now let's do a little bit of algebra with this expression. There's a factor of G on both sides, so we divide the whole equation by G, and those G's cancel away. And then let's divide both sides of the equation by the fluid density. So we got rid of the G, now we divide this side of the equation by fluid density, so that gets rid of this term. And now we've got a density of the block over fluid density on the right-hand side. All we have left on the left is the submerged volume of the block, and on the right is density of the block over density of the fluid times volume of the whole block. Now make it simpler by dividing both sides of this equation by volume of the whole block. So we have the volume submerged over the whole volume of the thing that's floating, and that's equal to the ratio of the density of the floating thing over the density of the fluid. And we come up with an interesting result here. The volume that's submerged, of course, is less than the whole volume of the block. So this ratio is less than 1. Which means this ratio is less than 1. The ratio of the density of the floating thing over the density of the fluid is less than 1. I'll say it this way: density of the floating object divided by density of the fluid that it's floating on is always less than 1. That's the necessary condition to have something float. If an object's density is less than the density of the fluid, the object will float. Ice has a smaller density than liquid water, so the density of ice divided by density of water is less than 1. Ice floats. And for most kinds of wood, the density of most kinds of wood is less than the density of water. So again, we'll have a ratio less than 1. So most kinds of wood will float on water. And we'll work more with all that stuff in class.